Hello, and welcome to this introductory video on power. In this video, we're just going to introduce this idea of power, explaining a little bit about what it is, and then provide you with a few ways of calculating it. So, what is power? For physics, anyway, power is all about the time rate of change of energy. That is to say that if we've got some interval delta t, and we measure during that interval that we had a change in energy of delta E, then that is what we're talking about. That's our power. And if that's nice and constant, then we're getting here just some single value for power. If these intervals are long and actually this rate of change of energy is changing, then we're talking about an average power here. If the intervals are really small, then we're talking about an instantaneous power during that teeny instant described by that teeny tiny interval. But regardless of whether we're talking averages or instants or whatever, this is the expression. Now we know that the change of energy is actually just equal to the work, so this is also just the rate at which you're doing work. It's just the work per unit time or per time interval that you've achieved. So it's how fast are you doing that work, or really, in some sense, how hard are you working to achieve that work or that change in energy. So looking at this thing, we know the units are going to be, for the energy, joules, and our time is in seconds. So the units of power are joules per second, which are equivalent. We introduce a new unit called a watt. All right, now that we've defined power, let's go ahead and consider the power that it takes to charge a capacitor. So, what is the work that we're doing, and what is the change in energy? Remember from the earlier video about the energy in a capacitor, for one individual little charge Q, it's just Q times V. And so if we're talking about the power being the change in energy divided by some time, then this is the power as we are charging a capacitor, okay, which happens to be at V, and we're moving this charge Q across it. This is the rate at which we are changing its energy, and so that's the power associated with moving that charge across. But what is a current? A current is a charge per unit time. So this thing here is exactly the current, so we could write that as I times V. Now this relationship P equals IV is a very important one, used a lot, but we can take it a step further as well. So let me just rewrite that because that's important. P is equal to IV. So that is important. I won't close the box because we're going to add more to it. So what about if I think now in terms of some actual circuit that is actually connected to my capacitor, which I was discharging, which was giving rise to this current I at a rate of Q on T. In that case, this current, if it's now flowing, say, over a nice ohmic resistor, then we know that Ohm's law will apply. So V equals IR. Put that here. In that case, I is just equal to V on R. And so I can replace the I in my expression for the power and get that the power is V squared on R. Okay, so that's another valid form. So connecting these different ideas, here I'm discharging a capacitor. That resulted in a current. That current, if it's passing over a nice ohmic resistor, is described by V on R. So for the ohmic circuit, I can also talk about the power as just being V squared on R. So the voltage across some resistor squared divided by its resistance gives me this value of the power. Okay? So those are some very important equations, very important forms for thinking about what's going on there with the power. Now, we can also play around with this. This is related to energy because power, again, is just the time rate of change of energy. So if I multiply the time interval to the other side, then I can talk about how much the energy of something has changed. And so I could go back and talk about the delta E is going to be P times delta T, and work from there to think about what's going on with the energy in some system that has a power P over some time scale delta T. What's happened to the energy? Okay, so some food for thought. When we go around and we pay for our utility bills, our electricity or our power bill, so to speak, it's actually billed in units of kilowatt hours. So have a thought, why is that? What does that quantity represent? Hint, it's on the screen already. And does it make sense that we're actually billed in kilowatt hours as opposed to, say, kilowatts or something like that?